Welcome to lesson 1.7, an introduction to functions. So right away, I apologize for the single letter typo in the title. It should be AN instead of IN right here. An introduction, not in introduction. An introduction to functions. So obviously we are going to look at the main idea for this whole lesson, functions. So the first paragraph here in your notes is the most important and crucial point to understanding functions. So first it starts with the definition. A function is a rule that establishes a relationship between two quantities called the input and the output. So first part of that, it establishes a relationship between two quantities, the input and the output. Then it goes on to say, for each input, there is exactly one output. So each input has exactly one output. More than one input can have the same output. So two different inputs could have the same output, but one input cannot have more than one different output. So a couple examples here are right here, an example of a function looking at the simple vertical input-output table. We have an input of 0, output of 3. Input of 1, output of 1. Input of 3, output of 1. Input of 4, output of 2. So even though the inputs of 1 and 3 share the same output, each input has exactly one output. So that is a function. What would not be a function is this example here with the input-output, where 0 went with 2, 1 had an output of 4, 2 had an output of 4, and an output of 7. So because the input of 2 has two different outputs, this is not a function. And then the other way that we can look at an input-output table would be horizontally. So this one here is also a function. And we have the inputs of 0, 1, 3, and 4, and the outputs of 3, 1, 1, and 2. So it's the exact same input-outputs as this table, just written two different ways. You can do a vertical input-output, or you can do a horizontal input-output. So one way to describe a function is to make an input-output table, as I just showed you. This table lists inputs and outputs shown in the diagram. So a vertical one here, horizontal here. The collection of all the input values is the domain of the function. And the collection of all the output values is the range. So the input values is the domain, the output values is the range. The table shows that the domain of the function is 0, 1, 3, 4. And the range is 1, 2, 3. So in writing the range or the domain, if something comes up more than once, for example, 1 came up twice in the range, we only have to write it once because we're just writing the different values. So you don't have to repeat writing 1. So example 1 is just looking at 3 different input-output tables and stating whether or not they are a function. So remember, for a function, each input has to have exactly one output. So if we look at A, we have 4 inputs, 1, 2, 3, and 4, and the outputs of 1, 3, 6, and 10. So each input has one output, so yes, that's a function. In B, we have the input of 1, 1, 2, and 3. But 1 has two different outputs. It has an output of 3 and an output of 4. So that would not be a function because one has two different outputs. And then for C, we have the inputs of 5, 4, 3, and 2, and the outputs of 9, 8, 9, and 7. So even though both 5 and 3 have an output of 9, each input has only one output, so it is a function. So then in example 2, it says, first make an input-output table using -2, 0, and 2 for the domain. So when we're making this input-output table, we are going to plug in a -2, a 0, and a 2 for our x values, because the domain is the input, and the input is always going to be your x value. So if we look at these three equations, we have y equals -2x plus 5 for part A. So we are going to create our input-output table. I just did a simple vertical table. And then we are putting in these three values. So a -2, a 0, and a 2. We are going to put those in for x into this equation to find out what the output of y is. So we would have first the input of -2. So this would become -2 times -2 plus 5. A -2 times a -2 is a positive 4. 4 plus 5 gives us a 9. So first, -2 has an output of 9. You don't have to put your work in the table. I'm just putting it here for the examples. If you want to do it on the side, that is fine. Then we plug in the input as 0. So we're substituting a 0 for x. So we have a -2 times 0, which is 0, plus 5. So that gives us the output of 5. And then we will substitute a 2 in for x. So we have a -2 times 2 plus 5. -2 times 2 is a -4. A -4 plus 5 is a positive 1. For B, we have, again, the inputs of -2, 0, and 2. And again, it's a vertical table, but it's slightly different. I just made mine as a T-chart. As long as it's organized, that's fine. You don't need to make the full grid. So I have my three different inputs for my domain. And then our outputs for our range, we had to calculate by substituting x into this equation. So y equals 4 minus x. So when we substitute in a -2, 4 minus a -2, when you're subtracting a negative, that changes to adding a positive. So 4 minus -2 is the same as 4 plus 2. And 4 plus 2 is a positive 6. Substitute in a 0 for x. 4 minus 0 is 4. Substitute in a 2 for x. 4 minus 2 is 2. So then our three outputs are 6, 4, and 2. And then for C, I made a horizontal input-output table. So all acceptable options. Input on top, x, output on bottom, y. And then we're putting in our domain, -2, 0, and 2. We're substituting those in for x in the equation, y equals 3 times x. So first substitute in the -2. -2 times 3 is a -6. Substitute in the 0. 0 times 3 is a 0. And then substitute in the 2. 2 times 3 is a positive 6. So our range would be a -6, 0, 6. So then example 3 is a tie-in to how we can use functions to recognize different patterns or represent them. So in this geometry connection, it says the diagram shows the first 6 triangular numbers. And you'll learn more about triangular numbers when you get to geometry. But all you need to worry about for this problem are our triangular numbers are 1, 3, 6, 10, 15, 21. And they continue along that same pattern. So those happen when we put in different inputs. So each figure here would be our input. So figure 1 would be an input of 1, and our output would be the dot pattern here with 1. Then we'd have an input of 2, output of 3, input of 3, output of 6, input of 4, output of 10, input of 5, output of 15, input of 6, output of 21, and so on. So when we make that into an input-output table, the figure number n is the input, so the input would be the figure numbers, and the output is the corresponding triangular numbers, which are here below the diagram. So our input-output table, I made a vertical. Here's our different inputs, and here's the corresponding outputs. So once we created that, then they want to know, in part B, does the table represent a function? Justify your answer. Well, when we look at the table, we know that each input has exactly one output. So yes, that would be a function. Then when it says describe the domain and range, we can simply write them as a numerical list separated by commas. So our domain would be all of our input values. So in this case, 1, 2, 3, 4, 5, 6. And our range are our output values, 1, 3, 6, 10, 15, 21. Example 4 is showing how this can be applied to a different scenario, word problem, with an equation, and you'll eventually see there's some limits to our domain. So first, let's look at the word scenario. You are at an altitude of 250 feet in a hot air balloon. You turn on the burner, and it rises at a rate of 20 feet per minute for 5 minutes. Your altitude h, after you have risen for t minutes, is given by the function. So our function has the equation h, our altitude, so the altitude equals the 250 feet we started at, plus the 20 feet per minute, so 20 feet times t, t being our time. But we know it only happens for up to 5 minutes. So that's where this limit to the domain comes, where 0, or I should read it as, where t is greater than or equal to 0 and less than or equal to 5. So where our time in minutes is less than or equal to 5 and greater than or equal to 0. So then it says, for several inputs t, use the function to calculate an output of h. So the way I did that was an input-output table. So that takes care of A and B. So what I'm going to substitute in for t, if my limits are 0 through 5, it only makes sense to go by each minute. So I substituted in 0, 1, 2, 3, 4, and 5. And what we're substituting those in for is t in this equation right here, h equals 250 plus 20 multiplied by t. So we'll be substituting for the t and then following the order of operations. So multiply by 20 and add the 250. So in our first substitution for 0 minutes, if we never turn on the burner, we would still be at 250 feet for our altitude. because 20 times 0 is 0, plus 250 is still 250. Then we'll substitute a 1 in for t. 20 times 1 is 20, plus 250 is 270. And then substitute in a 2. 2 times 20 is 40, plus 250 is 290. Do the same for 3, 4, and 5, and you get the outputs of 310, 330, and 350. So each one of these inputs, we're just substituting in for t in this equation to get our output of h. So once we've created our input-output table, they want us to graph the data graph the data from the table. Use this graph to draw a graph of the function. So what they mean by that is basically we're going to plot these points in a graph. So if we're graphing a change in an amount of time, it only makes sense to create a line graph. So you'll see down below, here is our part C for example 4. I took the information from the input-output table to create my graph. So in this case, there we go, zoom out. Remember that for any graph, we need a title. So I just simply titled it altitude of balloon. We need to label our y-axis, which would be the altitude in feet. And we need to label our x-axis, so time in minutes. So I put the labels with the units in parentheses because they gave them to us in the problem. And then my scale for the axis is, on the y-axis, I went by 50s for my altitude. So 0, 50, 100, and so on. And for time, I simply went by minutes, so 0, and in this case, up to 5. I just put 6 on there because honestly, I forgot. So in this case, then we just take our input outputs from the table. So back up here, 0, 250, 1, 270, and these are points to put on the graph. So over 0, up to 50, put the point. Over 1, up to 70, put the point. Over 2, up to 90, put the point, and so on. Then you simply connect the dots, and in this case, it creates what we call a linear function because the function graph is a line. And then, in this case, our domain. So for part D, what is the domain of the function? What part of the domain is shown in the table? So when we look at the domain is all of the t values, our input. So t in this problem would be the domain. But we know it's limited to 0 through 5. So in this case, the domain is all the values of t when t is greater than or equal to 0 and less than or equal to 5. So then if we were going to write the ones that are in the table, that would be 0, 1, 2, 3, 4, and 5, our inputs here. So then this box shows the 4 different ways we can describe a function in mathematics. The first way is an input-output table. The second way is describing it in words. So you could simply write out in words describing the function. The third way is representing it with an equation. And the fourth way is representing it with a graph. So again, we'll move down to example 5. So example 5, our word problem, or word scenario, is about scuba diving. And it says, as you dive deeper and deeper in the ocean, the pressure of the water on your body steadily increases. The pressure at the surface of the water is 14.7 pounds per square inch, or psi. so pounds per square inch is PSI, the pressure increases at a rate of 0.445 PSI for each foot you descend. Represent the pressure, in this case, capital letter P, as a function of the depth, lowercase d, for every 20 feet you descend until you reach a depth of 120 feet. So, this tells us a whole lot of information. So let's start to break it down. First, they want us to write an equation for the function. Well, if I have a word scenario to write my own equation, I can always start with a verbal model. So let's try to make sense of this word scenario. We know we're eventually representing a function for P, and P is the pressure at whatever depth. So P is going to equal something. So the pressure at any depth will equal our pressure at the surface plus, because it says it's a steady increase, so increases at a rate, so it increases at the rate of change multiplied by whatever our diving depth is, because it's for each foot we descend. So we're going to take the pressure will equal our surface pressure added to the rate of change multiplied by the depth in feet. So we have our verbal model, and then we can simply translate that to the labels. Pressure at depth was P, our surface pressure was 14.7, our rate of change was 0.445, and our diving depth was the lowercase d from the scenario here. So our equation would be P equals 14.7 plus 0.445 multiplied by d. And then I know where my domain would be limited. The way I know that d is greater than or equal to 0 and less than or equal to 120. They said the maximum depth is 120 feet. And if we're starting at the surface, we would be 0 feet below the surface. So our domain would be anywhere from more than 0 feet to less than or equal to 120, because that's the maximum depth we'll go to. Then for the input-output table, they tell us what numbers to put in for our input. They do that by saying for every 20 feet we descend. So our input is the letter D, or our depth, to get our output of P. So then our input-output table that we're creating, D is the input, P is the output. Because they said for every 20 feet, I made my inputs from 0 to 120 going by 20s. So we have an input of 0, 20, 40, 60, 80, 100, 120. Now what we'll be substituting those in for to get the output is the letter D in this equation right here. So 14.7 plus 0.445 multiplied by D. So you'll see here the inputs and the different outputs. Few examples. So first we'll substitute a 0 for D. 0 times anything is 0. So we simply get 14.7. 0.445 times 20 plus 14.7 gives us 23.6. Then 0.445 times 40 plus 14.7 gives us 32.5. And then you do the same with 60, 80, 100, and 120 to get the outputs of 41.4, 50.3, 59.2, and 68.1. And then for part C, it asks us again to make a line graph of the function. So we have our inputs, which are going along the x-axis. The input's always your x-axis, and the outputs for our y-axis. So the graph below, x-axis, remember, is this one. So the x-axis are inputs, so that gets labeled by depth. And the y-axis, the vertical one, is your output, which was the pressure. And then again, we knew the units. Pressure was in PSI, depth was in feet. Have to give a title to our graph, so I just titled it underwater pressure. Then our scale, I went by tens across the x-axis, so 0, 10, 20, 30, 40, and so on. And also with the y-axis, I ended up going by tens, so 0, 10, 20, 30, 40, and so on. Then taking our info from our input-output table, we're going to put our points. So over 0, up 14.7. So over 0, roughly up 14.7. Over 20, up 23.6. Over 40, up 32.5, and so on for each point. And then what you should get, if you graph them carefully, is a line in this case as well. So this output is also a linear function because we had a steady rate, which creates a line. So the key to all of this chapter, or all this lesson, I should say, not the chapter, comes down to understanding this piece here, this first paragraph defining a function, how to use input-output tables for your domain and range. Domain is always the input, range is always the output. And then also understanding how to create the graphs based on the different input-output scenarios and the 4 ways to represent a function.